As you can see from this previous explanation, segmentation has issues. It's very difficult to actually do best fit, first fit, next fit, or worst fit implementation. It's actually quite very heavy in terms of the computational powers you need to just do a simple allocation. The allocation, it complicates things very much, and at the end of the day you will end up with fragmentations that are like 1 KB and 1 byte, and I mean not 1 byte but 1 KB, for example, or half a KB or whatever. So you'll end up with small chunks of memory all over the place that are really hard, very hard to manage, and allocating data into these can be extremely hard, because for some data structures might even be larger than the chunks that you have. So that means that you basically lose a lot by just using the previous segmentation methodology, which was actually quite common. I mean, people used it. So people started, I mean, computer architects and operating systems programmers, they started coming up with the idea of memory pages, where you can virtualize memory with pages instead of just like a bunch of free heap / stack pieces all over the place. And pages is more like you look at your memory just like as if you have like a notebook, and each page you can write in each page whatever you want. So in this lecture, and well, in the rest of this lecture and in the coming lecture, we are going to actually look at how do we virtualize memory with pages. The basic idea is that instead of splitting up a process's memory address space into some small parts of code, into code, heap, and stack, variable sizes, logical segments, instead you would actually do something different. You would divide it into fixed size units, each of which will be we call a page, and you view the physical memory as an array of fixed sized slots, basically a bunch of pages, a bunch of page frames, each page frame containing one virtual memory page or more. Okay, so let's look at this simple virtual address space, which is divided into 4 pages, basically page 0 of the address space to a page 3, page 0, page 1, page 2, and page 3. Each page is 16 bytes and it has a fixed size. Okay, yeah, so in this very small example, you want to fit your code, your stack, and your heap in these 4 pages, because this is the virtual address allocation space that you have. I mean, in real life, you would probably have larger pages, because, well, your computers are either 32 bits or 64 bits, but let's just not look at that now. You know that a pointer to access data in this page structure will need 6 bits, basically 2 to the power 6, which is basically 2 to the power 0 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, and 2 to the power 4 is 16, 2 to the power 5 is 32, and 2 to the power 6 is 64, right? So you have 64 bytes. To access any byte, you need 6 bits, basically. So you map each of these virtual pages to a physical page. Okay, so the physical memory will also consist of a number of fixed sized slots. Basically, these fixed size slots can be either larger or equal to in size to the virtual sized pages, to the virtual page sizes. Sorry. In this case, you can use 4 pages. Okay, you have that your physical memory has 8 pages, and you're going to map your 4 virtual pages to these physical to these 8 physical pages. Okay, I mean, this is again a ridiculously small example, right? So pages of the virtual address space AS map to fixed size pages in the physical address space. In this case, you have mapped virtual page 3 to frame 2 to physical page 2, page 0 to page frame 3, page 2 to page frame 5, and page 1 to page frame 7. Okay, so this is basically direct mapping between virtual pages to physical pages. Okay, and to record where each virtual page of the address space is placed in physical memory, we use the operating system constructs something that is called pair process that is called the page table. Okay, and we'll talk a bit more about how page tables are used even later. The major role of the page table is to just store this mapping. Okay, page 3 for this process goes to page frame 2 in the physical address space. So you have a table that basically has direct mapping between virtual address to physical address pair process. Okay, and this is again will be part of your process struct of your task struct in Linux.